And we're live. Hello, Verge.
Hey, Mark. Welcome, everybody. It's Friday. Yay!
Yay! The necessary celebratory. I am Mark Corrali at Ryan High School in Denton, Texas.
And I'm Verge Cornelius at Lafayette High School in Oxford, Mississippi. I'm actually not at Lafayette High School right now. I'm
Well,
using the
yes,
same preposition Mark just used. But anyway, I'm at home. Same with Mark. And we have new little icons on our map, don't
there's
we?
us.
Yeah.
And there's
We're
our
so cute.
producer, and there's the watch party in Minnesota. Oh, I put it in Wisconsin. Oh, dear gosh. Sorry, Minnesotans. I'll move that over. I'm supposed to be in Duluth right now, so I should have put it up there. And
Uh-huh.
then I
There
hit
could be
Tucson.
there could be a watch party in
I
Wisconsin right
I
now. We
moved.
don't know.
I changed our map underlay, and I'm gonna blame that for now because
Okay.
I was working with a different map than yesterday. At least I caught it. That would have been horrible. Lutefisk versus cheese. I mean, there's a huge difference, right? In any case, we've got our review schedule keeps getting shorter as we keep ticking off these lessons.
The
Of
font
course,
keeps getting bigger.
yes, and we do have and I took the times off because if you don't know we're now, we're now. And then May 4th through 8th, we'll have exam prep and send off. And there's a little link to this calendar if you so desire. And then, of course, in the bigger picture, we are headed to that May 12th, 2 Eastern exam. It'll be 45 minutes long and 2 FRQs, a supersized and a regular maybe. Hopefully more information coming about that next week, actually.
And that's 2.5 weeks from today. So that is getting close. We need to start really cranking.
And the medieval times picture is doing much better than the outside the sushi place picture did, so that's good. And our overview of April 24th and this was both of us discussed this yesterday as we're getting into the review assignments. You'll notice the warm-up bullet has changed a little.
Yep. You're gonna just be expected to warm up on your own, and if we're just going to launch into wherever we left off the day before, just like in a regular classroom situation, planning a little bit extra, and if we don't get that far, we pick up the next day. So
in fact, we're picking up today where we left off yesterday.
Exactly right. But that might mean that I'm not going to tell a joke.
Oh no. Or maybe we'll find a reason. I think
I'm going to tell one right now.
Okay, tell one.
Okay. All right. How can you tell Thomas Jefferson was good at calculus?
Ooh, how can you tell Thomas Jefferson was good at calculus?
Well, he sent Lewis and Clark on an expedition to find the sea.
That's nice.
I've never heard that one before. I had a student send that to me.
so when they added the was that the Louisiana Purchase? Was that?
Yes. I looked it up. I did a little research.
So when
on
they
it
added the Louisiana Purchase,
it
must have been indefinite then if they had to find the sea, right?
Something like that.
They were not definite in that purchase.
By the way, I always crumple up the jokes and throw them in the sink.
Nice. So when your sink gets clogged up, you'll know why. Yeah. So here we are. And Verge, you did want to also start kind of discussing with the students, because I actually can't advance this slide. I have to steal the screen.
Okay.
About study practices. I think you said you wanted to mention.
Yeah, so in our shared folder for today, we have our notes template, which of course you can use to follow along. This, where Mark's going to start, is actually where we left off yesterday with this free response question from AP Classroom. So that's actually in yesterday's shared folder. So if you need to pause the video right now to collect some resources, that's fine. But 2.5 weeks until the AP exam. To me, I'm starting to feel a little bit like I need my students working every day. And what that means is they're not actually watching videos every day and taking notes. That would be like me watching football and thinking that I can go out and play. It's not the same thing. You have to sit down and actually make yourself practice. So even if that means like pausing the video, working the problem, and then checking to see if you got it right as we go. Don't just watch it and take notes because your teacher is asking you to. Yeah. Interact with it, practice. And then Mark, you had another idea too.
I was going to say, if you don't like the sports analogy, I mean, anything you do, right? Video games, music, I listen to music all the time. My son watches video game YouTubers all the time. But until you actually get out there and do it, you don't improve. You can get a little bit from it, but you're going to get better by actually doing, right? And so
Right.
it doesn't have to be sports, doesn't have to be music, doesn't have to be video games, but anything that you're trying to get better at, no matter what your pastime is, art, and so on. It's just practice is what makes perfect. And it's a cliche, but that's a cliche for a reason, right?
And it takes time. You have to set aside time to do it. And you're running out of time at this point. That's why I get like,
Yes.
ah,
Time to set the time.
time to start setting the time. That's right.
All right. And I may have a gray box up here, but I just know I'm going to be talking for a while, and I wanted to go ahead and get my background changed. Oh,
Okay,
no, it's
so
not here. Okay, you talk. Okay, there we
okay.
go.
So we see here a piecewise function, continuous function f defined for -4 to 4 inclusive. The graph of f shown above consists of 2 line segments and portions of 3 parabolas. Wow. The graph has horizontal tangents at x equals -1/2, x equals 1/2, and also at x equals something else that Mark's hand is blocking.
2.5.
5 halves.
So,
Yep, 2.5. It is known that f of x equals -x squared plus 5x minus 4 is that equation for that interval from -1 to 4. The areas of regions A and B bounded by the graph of f and the x-axis are 3 and 5 respectively. So A is 3 and B is 5. Let g be the function defined by g of x equals the integral from -4 to x of f of t dt.
right.
Now, that's a lot.
Yeah, there's a lot there, right?
And you need to take time to digest that mentally and underline things and mark things up. And that's going to be a whole lot different on the actual exam this year. But I think you're going to have time to digest. Don't just start rushing into it. Figure out where you are in the problem and then go from there. Okay,
And
Mark,
I'm going to scoot back and forth because I want
you
to
changed
be able to see
you
where.
changed your background, so now you're good. You can
Yeah.
go.
Yeah, you're fine. I had it done, but while you were still reading, I didn't want to take. You were doing such a good job. All right, so we're going to try and find g of 0, and we have our definition right here. So we're integrating from -4 to 0 of this function f of x, although they change it to t dt for that dummy variable that we discussed the other day. And that's what we're trying to find. So the way we find a definite integral, of course, if we can find the antiderivative, we can use fundamental theorem and do big F of 0 minus big F of -4. But in this case, what we have is the function itself. And so it's an area accumulation. We're going to find these areas. And I'm going to do the area from -4 to -1 because that's a triangle. And then from -1 to 0. So using those properties we alluded to yesterday as well, right?
Mm-hmm.
And then this is a triangle, and it has a height of 3 and a width of 3 as well. I think you can still see that on screen. And do pay attention to the scales because the x's are wider than the y's, but they gave you the point, that's 3 high.
He's saying that because I made a mistake on that earlier today.
And it's a very common thing to do.
Yeah, and so, I mean, I'm still doing calculus. I've been doing it for 30 years and I'm still making mistakes. So just be careful. Mm-hmm.
Yeah. So that triangle is 1/2 of 3 times 3. And this integral, well, that's this bounded area, but this is underneath the axis, right?
Mm-hmm.
So it's actually the negative a. It's the opposite of a. So it's -3. And if you really wanted to leave it like that, you could. But it is what 9 halves minus 3, so 3 halves.
Mm-hmm.
If you want to, that'll be useful later. So.
It will.
All right. And then they want g of 4 next. I know you can't see that, but you'll have to trust me that part A was g of 4. Well, g of 4 is going to be the integral from -4 to 4 of f of t dt or f of x dx. It actually doesn't matter once those bounds are filled in. Well, we already found -4 to 0, right?
Yep.
So g of 4 is going to equal this -4 to 0. And I wouldn't have to write all of this normally, but in fact, I'm going to stop writing it really quick. I'm going to do 0 to 1 because that's b, which I do know. And then 1 to 4 is the part where I'm definitely going to want more space than I've given myself, because that's the area under this parabola, that third parabola. So now I'm going to scoot up. I don't need that picture anymore. So G of 4 is going to equal the negative 4 to 0s are 3/2 that we found already. 0 to 1, that's B. This was G of 0. B has an area of 5, and it's positive because it's above the x-axis. And now, oh my goodness, some calculus.
That lower bound needs to be a 1.
It does.
Mm-hmm.
Thank you.
No problem.
Okay, now AP test, AP exam in a couple weeks. You could type that into your TI-84, your Inspire, Desmos, and get a numeric value. But we want to make sure you're ready for college, so let's go ahead and integrate.
In fact, if you don't know how to use your calculator for that, that would be a good thing to research this weekend.
Yes.
We're gonna talk about it.
We don't have time to talk about it this moment,
right?
But
we will.
It'll be touched on in the next 2 weeks.
Mm-hmm. So he's just
and I'm just plugging. Yeah, I'm plugging in my 4s while we were talking. Sorry. So I'm plugging in my upper bound, and then I'm going to subtract my lower bound, and I'm just gonna. I know multiplying by 1 is easy, so I'm just gonna try not to screw up everything else while I multiply by 1 in my head. Whoosh. All right. So we've got this big F of 4. This was our big F for if this was our little f. F of B minus F of A, and then we have 3/2, and I could stop, right? Boom. Mm-hmm. That's numeric. Yay. I put noses on my smileys. I know people think that's weird. Oh well.
I'm used to it now.
Yeah. Let's see. We're going to get negative 64 thirds, 80 halves, minus 16, plus a third, minus 5 halves, plus 4, distributing that negative. And can I just say 11?
Yes, please do.
Yeah, okay.
Please do.
I mean, this is 40. You can do
You're
the
good, Mark. You're good. Move on to B.
Yeah. I just want to talk about it. It's not that hard. This is negative 21. That's 40, and the 5/2 and 8/2 can get together. You can combine your fractional like terms and get there.
I love that. I do that all the time too. That's a good point to show them.
All right. So B, we haven't talked about B. B says, again, back to our original problem, find the absolute minimum value of G. And again, G is this integral we've been working with, this integration function. Find the absolute minimum value of G on the closed interval from negative 4 to 4. And closed interval, and this is justify. Closed interval min-max should bring to mind extreme value theorem or candidates test or both, depending on how you've discussed them in class. I guess I want to see my picture. So my candidates are my endpoints and my critical numbers. Now I can ignore the 1 because we're not changing signs there. It's not a relative min or relative max. But I'm going to go ahead and do the robust version where I'm just going to say, all right, G prime of X equals F of X equals 0. And that happens at, try to look at my picture one more time. It happens at negative 1, 0, and 1. So those are my candidates along with my endpoints. And here's where they've done us a favor, because we actually know a lot of these values, right? G of negative 4, well, that's the integral. We haven't done that one, but it's the integral from negative 4 to 4 of F of X with respect to X. F of T, actually, gosh, it really doesn't matter. Okay. It's 0. Negative 1, well, we didn't do negative 1 directly, but it was part of finding G of 0, right? G of negative, I said F of negative 1. G of negative 1 right there is just that 9/2. G of 0 we found, and that's, even though you don't have to simplify and you could stop here, sometimes you want to simplify because we have to compare the size of these numbers. And so you might want to do it now if you haven't done it before. And then G of 1 is the integral from negative 4 to 1 right here, which was just G of 0 plus B. So that's the 3/2 plus 5. And then G of 4 is 11. So, and what did we want to find again?
I was just thinking the same thing.
I believe it's the maximum, but no, the absolute minimum. Where's the lowest value? So I don't have to do 3/2 plus 5 because I know that's bigger than 3/2. So there's my minimum. So,
no, it's not, is it?
No.
There's a number smaller than 3/2.
Oh, there is. Oh my gosh, that's the interior. They got me. That's a relative.
It is a
There's
minimum,
our minimum.
but not the absolute.
That's right. G of -4 equals 0. And if they don't put an adjective on it, they want the minimum, right? So good. We caught that within 30 seconds. So no texts from the friends.
Okay. I'm like so paying attention right now. It's
and
great.
as far as justification, this is our justification. We tested our crits and our endpoints, and we compared those numbers and eventually did it correctly, right?
And I would say too that making that connection that G prime equals F equals 0, that's communicating that.
That's going to have to be said.
That's going to have to be said. That's part of your justification. It's not just doodling off on the side.
Because you don't want to just go through and say, I'm going to test every single integer value, because some of those are going to be really hard to find. And if you're going to try to do it that way, you're going to have to test all of them. And they're not all candidates, right?
They're not all candidates, right?
I guess in a way, every single number is a candidate, but we want to narrow it down. All right. Now C says find all intervals on which the graph of G is concave down and give a reason, which is not quite as hard as justify, but they do want us to explain what we're doing. So there's our little graph, right? Our happy graph. And this is F. And I am going to come back here and repeat this function. It is from -4 to 0. F of t dt is G. So we've already established that G prime is F of X. And I put this here, man.
I was going to tell you later, but
I've worked all these already, and it's just getting to be, I'm working ahead. All right. And so that means the second derivative of G is the first derivative of F. And that's what we want to look at for concavity, right? So, and again, I've already forgotten my question. They want concave down. So. And concavity is open intervals due to some textbooks definitions that can having to do with where the tangent line lives. So we only have to look for open intervals where F prime is negative. But they haven't really given us F prime. They've given us G prime. So I want to talk about G prime. So we're looking for where this is decreasing. Because if that's decreasing, then this will be negative. So it looks like at -2, 3, we have a peak, and we come down to that horizontal tangent, and they told us in the stem, oh my gosh, they gave us information, we're going to use it now. So from -2 to -1/2, we are decreasing along F or G prime. So we are concave down. And I'm not a big fan of abbreviating those terms. It's where you're trading 25 or 15 minutes for college credit. You can write all 10 letters. 11 letters. Okay. Then we're increasing up until 1/2. Again, this is happening at x equals 1/2. Decreasing until 1. And then this peak they told us was at 2.5 or 2.5. And decreasing until we get to 4. And my reasoning is because G prime, which equals F, is decreasing on those intervals. So, and I think I actually got all my signs right, which every time we've had a -1/2 and a 1/2 on a graph for the last 3 days, I've screwed up that sign to begin with. So. All right.
I don't know if you want to put another comma in between those two.
Oh, right over here.
Yeah. It's not a big deal. But
comma.
yeah.
I do
So
like my culture clubs. So.
yeah, come a chameleon. Da-na-na-na, da-na-na-na. So, okay, so that was the free response question, kind of leftovers from yesterday, just like how we eat these days. We're eating
again,
the leftovers from last night.
Yeah, if you recognize it, it's from AP Classroom. It's one of the questions that actually students have access to now without teacher permission. If you go in there, there's some green bullseyes that you guys can access without having to have you. If your teachers have never used AP Classroom, and you're curious what's up there, there's some stuff up there for you, even if you haven't used it.
So what Mark is getting out now is what's in our shared folder for today, Friday. Go ahead and start with number 6, Mark.
That's right. And I also wanted to remind you that on Wednesday, I try to do the keys 2 days behind. I actually had those written up but not typed, and I have to type in one more answer before I put that in the Dropbox, but that will show up this afternoon.
So today, when we made this schedule, like, back in March, we wanted to do a mixed bag review. And so this page and notes, 2 pages of notes, is a little bit from each unit with the unit identified. And this is the last time we're going to actually identify what unit something comes from or what even the name of it is, because that's really a goal in the next couple of weeks, is just to be able to do it no matter whether you're told, hey, differentiate, hey, integrate, now this is a limit question, whatever. So this is something that I know a lot of people want us to work on. So I thought we'd do this one for sure.
You're actually
first.
changing the order from our plan this morning.
No, we were going to do 6, 1, 2.
I thought we were going to do 1, 1, 2, 6, but just get all the limits in at once. But it's fine. It fits with the accumulation well.
Yeah.
In any case, let me move you so I'm looking at the camera when I'm looking at you.
Okay.
Okay. So, where were we going with this?
Well, this has come up on, like, it was on the Big 10 yesterday that we worked on, and they were and we didn't do any of those problems. And some people I've had students emailing me saying, when are you going to do the sigma notation review? My teacher didn't teach it yet, So here comes Mark. He's the one who really taught it to me back when it came on the curriculum about 4 years ago. I had completely forgotten it. So he could teach it to everybody else too.
Yeah, and it's funny because I always, whenever anyone says put in the curriculum, I was like, put back. It was there. It was there in the 90s and 80s.
True.
But it had been gone for a while.
But I forget, like, if I haven't done it in a year, I forget it anyway. So
this is actually what you're doing every time you do a definite integral. This is what you're actually doing. These two things are equivalent statements. This is not like, ooh, this is a handy thing that this equals this. This is what you're actually doing when you use that fundamental theorem of algebra, or the fundamental theorem of algebra calculus. Although the fundamental theorem of algebra is cool, and we use it as well. But so this is the big draw, right? As we go from drawing little rectangles under a curve, and that's what this is. This is rectangles. We'll talk about how to find them in a second, and we're getting to here. So that's about what? That's about like 3 weeks of work right there. So the way I look at these, the limit as n goes to infinity. N is your number of rectangles. And the common question we ask in calculus and you'll see it in Calc 2 especially, the BC kids have gotten sick of this, is how are we going to get a better approximation? More of whatever we're doing.
More, but smaller.
Yes, more and smaller. And tiny things. All right. So we're adding that. This is the sum. So we're adding up, right? We're adding up a bunch of rectangles. And these are our heights. And these are our widths. And so that delta x, if I come back to here, the width of each is just going to be the width of the interval divided by how many rectangles, because n is my number of rectangles. And then if I'm doing a right-hand Riemann sum, which is how we typically do these because they're easier to set up, I just start marching across. And I start at A and I just add one of these. And then I add another, and I add another, and I add another. And so I have these values of x, which I put a sub k on, that are delta x, that start at the left endpoint, like I said, and you're adding delta x k times. So you add one of these, add 2 of them, add 3 of them, until you get to n. Of course, n's going to infinity, so we need something else. And then f of xk, that gets you the height because you're plugging it in. So that's why that's the height again. So how do I use this? Well, that's great, Corelli. Now what? All right, so I'm going to try and keep this on screen if I can while I do this. and I'm going to start working, and Verge can make fun. I'm going to change colors.
Well, you can even push it up a little bit if you wanted to fold it.
The,
No.
I can and I can't. All right.
Okay.
So I'm looking at, this is probably my height and this is probably my width. Now there are actually an infinite number of shifted versions of this definite integral that will all get you the same evaluation, but we want to make it as easy as possible. And so I'm going to look at that as my delta x. So that means my width of my entire interval is pi, right? Because that's pi divided by n. That's my b minus a. Getting a little fuzzy. Okay. Well, then I look for, where does this get operated on? And I'm sorry for the small print there. These pens are not as fine tip as my gels, but I can't fight this feature, right?
Maybe version 2.0 will be.
So I look at this, here's pi over n times k. So there's my delta xk. So that right there is 0 plus delta x times k. I just found my left bound. And if it's pi y, I know it's 0 to pi for the bounds. And I know you're thinking, oh, it's not going to be that easy. And yes, it is going to be like set up like that in the real test. This is what they're testing on, is if you can read this. And then it's in my function. This is f of xk, so everything else is my f of x. 3 cosine of x plus 5 with respect to x. And then just like Verge said yesterday, when we do an antiderivative, we should mentally take the derivative to check it, right? How would I build delta x? Pi minus 0 over n. Boom. That's my delta x on the end. Then I would do left endpoint plus this times k and plug it into my function. And I have 3 cosine. There's my 0 plus delta xk plus 5. It works. So whether it was the author's intent or not, this is our function. And now it says evaluate the limit. And you're like, oh, I have to work this out. No, because these are the exact same thing. So to evaluate the limit, now I can jump to the fundamental theorem of calculus. So
and by the way, he did rewrite it as a definite integral. That was the first prompt, was to rewrite it as a definite integral, and he did it. Check. Now he's going to evaluate. He's going to evaluate the easier one.
Yep. So 5x, right?
We're not going to be here all day with all these infinitely many rectangles. No.
Yes, yeah. And there are rules for evaluating that. Today I care not. I care deeply, but not today. Derivative of sine is cosine, so I'm good on that.
He's going backwards.
Yep, going backwards on my derivatives, make sure I get my SIGN in front of my SIN correct. And then we're looking at 3 sine pi plus 5 pi minus 3 sine of 0 plus 5 times 0. Am I still on screen? Yay.
Yes.
Numeric answer, fine to stop there. Sine of pi is 0, sine of 0 is 0. The answer is 5 pi, but you can stop there or you can stop there. And yay.
Yay!
And I don't think this will be the last time we talk about these.
Absolutely not.
But there's a quick introduction, and like I said, this to me is the key. Is just building this habit of what's my delta x. So where are my stops and what are my heights? All right, now we're going to go to number 1, correct?
Yes.
Okay.
Sorry.
No, you're fine.
This is another one that we've had a lot of requests for, especially from teachers, because they can do limits all day long, but there have been some AP items that were limits of compositions of functions. And so I said, well, we don't need to review limits like we did that.
We didn't want to do this in Unit 1 because we didn't want to scare everyone off.
Right. We don't know enough in Unit 1 to do this. So, but this really is limits and continuity. It's just like, you know.
And I love these. I can write these all day long now, which I was not when I first saw them. But all right. So we have the piecewise function f of x. It's made of 2 line segments and a semicircle. We have our semicircle and our 2 line segments. And it's shown from -4 to 5. And I think that's wrong.
I just noticed that. Yeah. I think
we flipped the graph yesterday. We flipped the graph and we missed our
And we didn't
domain.
do the,
So I'll upload a corrected version. So the limit is x is 0 is of f of x minus 1. So it's a composition. If functions are continuous and their limits exist, we have a whole bunch of properties and we can just plug in. So I can do the limit, off to the side. This is all happening mentally, right? Behind my face, probably. The limit as x approaches 0 of x minus 1 is just -1. And then, so what I'm really doing, and I've done this, and Verge has seen me do it, I actually do a u sub sometimes and say, I'm going to let that be u. Now, remind me again, what is a limit?
It's like a y value that the function is approaching.
That's way too small. I apologize. This is a thought bubble work, so I'm being sloppy about it. All right, so the limit is what you're approaching. So u is approaching -1. So I can rewrite this as the limit as u approaches -1 of f of this function u. And then, so u is approaching -1. So I look over here as f approaches -1, the curve of it, the value of f is going to approach 0. And this is one, because f is continuous at that interval, it's continuous right around both of these numbers, I can just plug in, just go f of 1, 0, f of -1 is 0. So that's all fine and good, got to use my properties. Those don't bother people very much. The next one.
Can I just say, like, those don't bother people much because many of us are very good at transformations, and we could say to ourselves, oh, that's just the function shifted to the right one. So I'm just going to shift it to the right one. And then I'm going to look at the limit as x approaches 0 of that graph shifted wholesale to the right one.
Right.
And then I can see where that kind of cornery cuspy thing is coming in at 0. And so my y value is 0 coming from both sides.
I think realistically what a student does is plugs in 0, finds f of -1 and writes down the answer.
Yeah. So
and that works if it's continuous at that point, right? So now we start talking about this. If I plug in 0 into f of 2 minus x squared, well, f of 2 is 3, but f of 2 from the right is approaching -1. We have this two-headed monster here where the limit does not exist at 2. Unfortunately, we should have moved that hole down here. We should have moved the hole up so people would get it wrong. 2 minus x squared graphically. Verge, what does 2 minus x squared look like graphically?
Upside down parabola. Vertex is at 0, 2.
Yeah. So as x is approaching 0, this function is approaching 2. So I'm going to do this thing where I say, all right, u is going to be the limit as x approaches 0 of 2 minus x squared, and it equals 2. So now I can rewrite this as the limit f of the function u, and u is approaching 2. But the limit is of number approaches 2 of f does not exist. So we need to do a little more investigation. Notice which way we're approaching 2.
We're approaching it from underneath. So those y values are always less than 2. So we're approaching 2 from the left.
Right. Yeah, underneath on this graph translates to, on the inverse or whatever, it translates to from the left or something like that. I guess I could, but yeah, so this changes our game. So now I can put that from the left here. And as I approach 2 from the left, my function value is 3, or my function value is approaching 3. You can also do a table approach on this, where if you do things like, as we're approaching u, if this is x and this is 2 minus x squared, as I come from the left, I'm going to be getting things like -1.99. And from the right, I'm going to be getting things like -1.99. So I can see that I'm approaching from that underneath or lesser values. Any other questions I should address on that, you think, before
should those be -1.99 or should
no, they
those
shouldn't.
be positive?
I was inserting the negative exponent, wasn't I? Silly Mark. Okay.
Oh gosh.
Yeah, because we're subtracting very small numbers from 2, so we're getting numbers that are just under 2, right?
I think for for people who are watching this, I picked up on something, and Mark picked up on something, and that is that really the point on the graph should either not be there at all, or it should be underneath the, it should be in the fourth quadrant. In other words,
I think when I change these, I'll move that hole.
yeah, move the hole. That's exactly right. And I think, so yeah, so in fact,
So that
darken it right now, Mark, so that it's obvious what it's going to look like on the, yeah. Because otherwise you're getting it right for the wrong reason. And I always say that to my students, make sure you have it right for the right reason, because otherwise you don't know what you're doing. You know, you're kind of like halfway there, but you don't really know how to do it.
All right. So our last one, man, we are killing time today. Sorry, I'm going
That's
slow.
Okay. These are good problems to do. And I'll do the next one if you want the unit 2. Okay.
So here we go. We're doing, this is what this first function looks like. We're doing a product now instead of a composition. F of x minus 1 is the one we already did up there, right? It's just that shifting this function 1 to the right, as Verge said. So we know that this is approaching 0. But this function, the limit does not exist. And so I can't break this into 2 limits and say this limit times that limit, because the property says I can do that if both limits exist. And
but you could,
yes?
But there's something else you could do though.
Yes.
You could do it one-sided.
Yes.
You can investigate it one-sided. Yeah.
I actually have a page of notes on this that I may make available in the Dropbox later, because I have many examples of this for you to play with. Yeah, so if we just do the limit from the left, now I can use the property.
Yeah.
Because the limit of this exists from the left and the limit of this exists from the left. So for this, I can just say the limit of that from the left is -1, and the limit of that from the left is 0, because since the limit is, right, the limit at 0 is 0, then the limit from the left has to be the same. And then if I do the limit from the right, is going to be, actually, I'm going to write that as -1 times 0 equals -1 does not equal 0 this week. Okay. And then from the right, I'm approaching 1, and the f of x minus 1 is approaching 0. And so the limit from the left is 0, the limit from the right is 0.
So this limit exists.
If those are the same, then the limit as x approaches 0 is what the left and the right both equal. So, and that's another, and 0 doesn't always win that game. So you got to make sure, because there's ways to create that so it's indeterminate and things like that. But basically the idea on all these is, on these two, is you can't use those if-then properties, because the if is the limits both exist. And if they don't, then you have to find another way to explore them, like either by translating this into a one-sided limit or translating this one into 2 one-sided limits.
Yay, those are some really challenging topics. You want me to grab the screen, Mark?
Yeah, go ahead.
Give you a break to drink your coffee? Okay.
It's getting lonely.
It's getting cold. And we're not going to keep you too much past our normal 45 minutes.
Uh-oh. Maybe I am doing number 2.
With our
there you go.
No, I'm here.
Okay.
We're not going to keep you. We're not going to keep you much past our 45 minutes, but we did check with our producer because we knew that we had an ambitious amount to try and get done today when we scheduled this back on, what was it, March 20th or something?
27th, I think.
But,
oh, no, you're right. Yeah, 20th.
Yeah.
Right, you're right.
So unit 2, in terms of all of our different units, unit 2 was differentiation, everything except chain rule, basically. So product rule and quotient rule are kind of the 2 biggies there, plus the derivatives of things like e to the x and natural log of x and sine x and cosine x. But this one I picked on purpose, or I wrote it on purpose, because I really wanted students to engage with this kind of question, and teachers, and realize that on the AP exam, you could be asked this question, but nobody's going to tell you it's about differentiation. And you're going to think, oh, it's all about limits, but it's kind of not, you know, like Given f of -3 equals 5, f prime of -3 equals 2, g of x equals 1 over x, let h of x equal this function right here, 4f of x times g of x. We have to find this limit. Limit as x approaches -3 of h of x minus h of -3, all divided by x plus 3. Well, the first thing when you're faced with a limit like this, especially when you have this symbolic here, you might go ahead and do a direct substitution. H of -3 minus h of -3, get 0 in the numerator. Denominator, -3 plus 3, get 0. Dang, I'm going to have to do something else. Well, back in these times, you didn't know about L'Hopital's rule. You might have known about limit definition of the derivative, though, and you also might have known the alternate definition of the derivative. Which one is this, Mark? Is this the limit definition of the derivative or the alternate definition?
Well,
of the derivative?
it's the alternate limit definition, right?
Right, right. They're both the limit definition of the derivative. That's
But
right.
this is the alternate because it's specific to a point, not in
Mhm.
terms of h and x.
Right. But you know what? When I was in high school, I didn't know what things were called. I just knew what to do. You know what I mean? And so it's okay if you don't know what it's called, but I think I know what to do. I can either use L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator and try my direct substitution again, or I can recognize that this is that alternate form of the limit definition of the derivative and that this is actually equal to h prime of -3. Okay. Either way, the upshot is that I'm going to have to figure out h prime of -3, because if I did L'Hopital's rule, and I'm not doing any sort of justifying or anything here, I'm verbally confirming that I can do L'Hopital's rule. What happens is the derivative of the numerator ends up being h prime of x. The derivative of the denominator is 1, and then just end up with the same thing. I'm looking for h prime of -3. All right, so here we go. I got to take this function, I have to differentiate it. And I'm going to use product rule. So I have to do h prime of x is equal to 4 f of x times g prime of x, and then plus g of x times 4 f prime of x. That's product rule. And first times the derivative of the second, plus second times the derivative of the first, however you have it memorized, whatever works for you. Get it down symbolically, and then start plugging in. In fact, I would actually do another line here so that you don't tangle yourself up too much, because there's going to be a lot of, it's almost like picking stuff off the shelf or something. You've got to go up here and do this and over there and do that. So I like to plug in this -3 before I start plugging in things like 5/2 or 2 or something like that. All right, so h prime of -3 is going to be 4 times f prime of, or sorry, 4 times f of -3. Do we have that? Yep, we do.
Yeah.
Okay, what about g prime of -3? Do we have that?
Well, I do. But no.
I thought you were just hanging out over there, Mark. Okay, so
Yeah,
what do
the
you have for
Dropbox is
g prime?
updated by the Dropbox is updated. So if you guys
Oh
want
yes,
to,
because there's like 4 marks out there. There's like the Dropbox mark, the doing the calculus on the side mark. Okay.
So the domain and whole is correct on F now, and then you know one question.
Okay. So what was g prime of x?
Well, it's going to be the derivative of 1 over x, so -1 over x squared.
Okay. So then g prime of -3 would be -1 over -3 squared, so -1/9. So
Yeah.
this is times -1/9. And then plus g of -3. Don't have that either.
Just
Okay.
-1/3, yeah.
Right. G of -3 is -1/3. And then times 4, and then times f prime -2.
Yep.
Okay. So this is a happy way to leave your answer. Again, many times we want to confirm that we have a reasonable answer. I don't know where this even came from, so I don't know how reasonable my answer is or isn't. I don't have to use this later on in a problem like Mark did earlier today, where he had to then bring that 11 into another problem. So I might really want to leave it. But I know there's people out there who are just like, dying if things don't get simplified. So I'll just appease them and hopefully do it correctly. So I have negative 20 over 9 plus 8/3. And I believe this ends up to be positive 4/9.
I think that's what we got earlier today, at least.
Okay. Yeah. Okay. So we're going to stop there. On Monday, we will pick up with these chain rule problems, which are quite delicious, I must say. And then I'm serious.
I know, just the choice of descriptors.
I mean, okay, this is true. I wake up every morning before my alarm. I turn on the coffee, I let the dogs out, I feed the dogs, I sit down with my coffee, and I cannot wait to work the calculus problems. There is obviously something wrong with me, but I hope that everybody who is listening right now
I'm
sorry,
I'm going to interrupt and say it's funny that I have this license plate frame, right?
Yeah. Wait, you gave me one though. I have one too in my classroom.
You don't have the frame though.
Oh, the frame. You teach AP calculus, you have problems. But yeah, but I mean, like, I hope that everybody listening right now finds something that really wakes them up in the morning and makes them enjoy, doing that kind of thing. That's the best we can do in our lives, is find stuff that brings us joy. And this is definitely something that makes me very happy. But we will work on these on Monday. It would be great if you worked on them before we even start going over them, because then you could really be checking yourself. So you know what might be good to put in the Dropbox as well, Mark, is your circuit on the sigma notation.
Okay.
They would love that. Teachers and students would love that.
I'll include the notes page that goes with it too, which just summarizes what I did. So
we have work, but it's not in the shared folder in real time right now, but it will be, especially for the thousands of you who don't watch us live, who watch us later. But anyway, we'll see everybody on Monday. And thank you for watching. We're trying something new, so I got to mute myself in my video. So bye.
Bye, everybody. Thank you. See you. Have a good weekend.